Let's take a look at what we meant by high spin and low spin complexes. So in the case of the example that we have, CO2 plus, the electronic configurations will end with 3d6. So with 3d6, the electronic configuration is as such. In this case, this will be deemed as a high spin, as most of the electrons are not paired. Alternatively, you can have a low spin configuration where all the electrons are packed into orbitals, ensuring that 1d orbital is fully filled before occupying the next, and more importantly, each orbitals are fully packed. So this will be deemed as low spin. And if you are asked the energy gap of the d to d splitting in the high spin and low spin complexes, we will argue that the energy gap in the low spin complex will be of a higher energy level. The reason for that is as follows. In the case of the low spin, only 3d orbitals are required to house the 6 electrons, meaning to say there will be 3 2d orbitals that will now be able to hybridize with the 4s and the 4p orbitals to form 6 empty orbitals to house the 6 lone pair electrons of your ammonia to form the complex. Hence, in summary, the 2d orbitals are now of a higher energy level. The 2d orbitals, in order to hybridize with 4s and 4p, must now be promoted to a higher energy level. Hence, the energy gap will be wider. Let us now take a look at another example, FE2 Plus, when it is low spin and when it is high spin. Electronic configuration of FE2 Plus is also 3d6. So in this case, when it is low spin, we will ensure that electrons are paired in each orbital. So in this case, only 3 orbitals are required to accommodate the 6 electrons. However, in the high spin, all the 5 3d orbitals are being occupied. Let's now take a look at another example, FE3 Plus. FE3 Plus has an electronic configuration as such. So in each of the 3d orbitals, there are 5 electrons. So in the case of a low spin, we will pack all the 5 electrons in 3 orbitals, whereby one of the orbitals is half filled. The other 2 are fully filled. In the case of high spin, all the 5 electrons are all singly occupied. So in this case, like earlier explained, 2 of the 3d orbitals which are not occupied in the low spin complex could now be hybridized with the 4s and 4b orbitals to accommodate lone pair electrons from ligands. Therefore, we expect their energy level to be higher, and this due to d splitting is represented in this diagram here. Conversely, in the case of the high spin complex, the diagram that represents the d to d splitting is as such, where in this case is as such, and where in this case the energy gap is lower. The energy gap is deemed to be lower the other way to explain why the energy gap is lower for the high spin complex is that when the energy gap is small, it means that electrons, if fully paired, are unstable since they electrostatically repel each other. And since the energy gap is low, and as a consequence of the electrostatic repulsion, the electrons will promote themselves to a higher energy level in order to be singly occupied to attain greater stability. Hence, in conclusions, we have 2 further examples to illustrate here. Again, showing that the low spin complex contains fully packed orbitals, and the high spin complex shows that all the d orbitals are singly occupied. Note that it is important in the high complex ion, the energy gap is small, so that each electron can be singly occupied and not have inter-electronic repulsion forces between electrons in the fully occupied orbital. While in the case of a low spin complex, the energy gap is large, as the 3d orbitals are now hybridized with higher energy level of the 4s and 4p to form hybrid orbitals to accept lone pair electrons of ligands.